We looked at derivatives of vector functions. Now we're going to look at integrals, and then we'll go over some examples for both derivatives and integrals. The derivative or the integral is extended in the same way as derivatives. So when we look at definite integrals, the same idea follows here. That is, a to b of a vector valued function can be evaluated as the integrals of each of the components in the I and j and k direction, and then combining them as a result. And the fundamental theorem also gets extended so that once you have the antiderivative given by capital R, similar to capital F that we used in regular two-dimensional calculus, and then it's this evaluated at the two endpoints B and A. Okay, so let's look at a simple example for finding the integration. 2 cosine t I cap plus sine t j cap plus 2t k cap. If you're finding the indefinite integral of this particular vector function, then all we have to do is find the integrals for each component separately. So we have 2 sine t I cap minus cosine t j cap plus t squared k cap plus c. Now, similar to one dimension, this is a constant vector that we have to add. And if this was 0 to, say, pi over 2, then all we are doing in the end is plugging in these values to get, so sine pi over 2 is 1, so we get 2 I cap minus cosine pi over 2 is 0, but cosine 0 is 1, so this becomes positive 1 j cap plus this becomes pi squared over 4 k cap. So the integral of this vector valued function is given by this particular vector over here. Now let's look at some examples for derivative. So going back to derivative examples, suppose I have RT is given in this form, t sine t I cap e raised to t cosine t j cap and sine t cosine t k cap. Well, then finding the derivative is just going to be product rule, and product rule. So I get 1 sine t plus t cosine t I cap plus derivative of e raised to t is e raised to t, and the derivative of cosine t is negative sine t. J cap, derivative of sine t is cosine t times cosine t minus sine t k cap. So this is going one step further, and writing it in the other notation, not the ijk. This is et cosine t minus sine t and cosine squared minus sine squared. So okay, let's look at a slightly different kind of example. Says find f prime 2 where ft, not a scalar function, it's a vector function, and that's because it's defined as the dot product of these functions, where the value at 2 for u vector is the following. The derivative is this, and v is given as the expression t squared t cubed. Okay, so for this we will use the result about the derivative of dot functions, of the dot product. The structure of all of these is, the basic structure is that of a product rule. So you take one with a dot and you keep right. So we want to find f prime at t equals 2. So I need u prime at t, I need v at 2, I need u at 2, and I need v prime at 2. So let's see, u at 2 is given to us as the vector 1, 2, negative 1 dot. V at 2 can be found by plugging in 2. So 2 squared and 2 cubed plus u at 2 is given as 1, 2, negative 1. Oh, I made a mistake. This is u prime, so this should be 304, and dotted with v prime at 2, which we can find v prime is going to be 1, 2t, which is 4, and 3t squared, which is 12. So dot product means this is 3 times 2, 3 times 2 plus 0, 4 plus 4, 8 plus 1, 1 plus 2, 4 plus negative 1, 12. So this is 6, 0, 32, 1, 8, negative 12, 38, 39, 47, minus 12 is 35. Okay, so those differentiation or derivative rules that we looked at can also be asked in this particular way. Okay, so that was another example. That brings us to the end of this derivative and integral part. Now, of course, in the next section, we will be using this to apply it to things like arc length, finding the arc length function. We define something called the curvature of any given curve, and there are some other applications that we will be looking at. Okay, so that's it for this particular video.